colóquio do Instituto de Física da USP. Eu gostaria de pedir desculpas. Nós tivemos um pequeno mal-entendido acerca do horário, quando o professor Kurtz foi convidado. O fuso horário, a diferença de fuso horário era diferente, depois acabou o horário de verão na Alemanha, e por isso ele acreditava que a palestra começava 1 hora mais tarde. Então, é um prazer tê-lo aqui, e eu vou passar para inglês para que ele possa nos compreender. So, I would like to ask Professor Henrique Barbosa, who is a collaborator who knows Professor Jurgen, for the introduction and to handle today's colloquium. Henrique, please.
Thank you, Paulo. So today in the Physics Institute Colloquium, we have Professor Jurgen Kurtz, and I will say just a few words about him before we start. So Professor Kurtz has a degree in physics and mathematics, and he is a professor of nonlinear dynamics at the Institute of Physics at the Humboldt University in Berlin. But he's also held positions in different places. So for instance, he's the chair of the Complexity Sciences Department at the Potsdam Institute for Climate Research. And his main focus is on nonlinear physics and complex systems and their applications in different problems. So it could be Earth system, physiology, biology, engineering, among many others. So Professor Kurtz has built in his career a large network of scientific collaborators around the world, and he has advised over 60 PhD students. And they come from all different countries, from over 20 countries. And Professor Kurtz has a huge publication history, in having published more than 1,000 papers, 8 books. And just to give one number, I mean, that he has over a dozen papers with over 1,000 citations each. He is on the editorial board of many scientific journals and received innumerable prizes and awards. To mention just one, he was elected fellow of the American Physical Society a few years back. So without further ado, and having said these words, I would like to thank Jurgen for accepting our invitation to talk to us today, to give this colloquium about complexity and how it meets climate, and what's behind the Nobel Physics Prize of these years. So Jurgen, thank you very much for accepting our invitation and be here today to talk to us.
Yeah. Thank you very much, Enrique, and I'm very happy to be with you. For me, it's in the evening, and for you is at the afternoon. Was some misunderstanding with the time, but it's okay for you. I will talk a bit about a combination of complexity and climate. And usually I start my talks and try to convince people that modern concepts of complex system science, of statistical physics, are useful for earth sciences. But this is now much easier for me, because this year the Nobel Prize was given to 3 people which have done a lot for climatology, especially for climatology, Klaus Hasselmann and Manabe. Giorgio Parisi, you all know, is very strongly in statistical physics, and he applied stochastic resonance to the explanation of ice ages. But I will talk more about the other 2. And the general laudatio was for their work on describing complex physical systems. That is very nice. But also pioneering mathematical model of Earth's climate. And this is now the clue, predicted that increasing levels of carbon dioxide in Earth's atmosphere would raise global temperatures. This I will explain in a bit more detail, but let me start with the general problem of weather forecast, of climate phenomena. This is, of course, a long-standing problem. It was for for a very long time, mainly statistical based, but the first who made it really physics based was Louis Frei Richardson. He wrote already in 1922 a book, Weather Prediction by Numerical Processes. And that means he really considered the Navier-Stokes equations and all the balance equations, brought this in for weather prediction, and he understood one needs numerics because you cannot solve these equations. They are too complex and too difficult. But he was too early with this because he had no computers, and it needed about 30 years till John von Neumann came with his group, till computers came, and then they brought it really to practice and made then physics-based weather prediction. That means equation-based weather prediction via numerics, of course. This was a big, some revolution, if you wish, but there remained a problem, a basic problem, understanding the basic underlying processes and reasons, especially for climate change, which have come into the game later on. And here the pioneering contributions by Hasselmann and Manabe set in. Klaus Hasselmann, he felt always as a physicist and a mathematician. He studied deeply fluid dynamics and so on, and worked then mainly in applications to climate, but his background is really statistical physics. And this he used, and a special problem he solved was when you calculate the power spectrum of climate signals, you have a component that's the peaks. There are, of course, peaks, the annual and the daily peak, but you have always a noise floor. That means there is some noise underlying, and no one could explain. This was called the red noise problem. No one could explain what is the reason for this. And Hasselmann considered this really as stochastic part. He was the first to consider a stochastic part in the weather and climate modeling, and especially the rather short period weather dynamics he considered as a random process. And that means he had an analog of climate system to Brownian motion, means to random walk response characteristics as large particles interacting with an ensemble of much smaller ones. This is what Einstein solved in 1905, but he brought this approach to climate. And this was really genius. And he came then to modified equations, diffusion equations. And here you have this V and D are the typical propagation diffusion terms, and they are dependent on time in his models. And he considered then this Fokker-Planck equation, solved it in some sense, and what he showed, one point was, he showed that the climate is not predictable over a long time. It is really, the predictability is limited. And this was the first for rather realistic climate models. We know Lorentz did it in 63 or so, Hasselmann 76, but Lorentz for this very simplified model where he took only one periodic component in the equations or out of the equations, and then came to the three-dimensional ordinary differential equation system and found there this limited predictability. But here you see is much more realistic, and he showed that Hasselmann, that's also limited predictability. And also he solved this, what is then now called red noise problem, that this is due to really intrinsic climate and weather dynamics, such that one can explain also now the such power spectra, which was not explainable before. And then he also studied in more sophisticated models, in coupled ocean atmosphere models. He analyzed then what is the influence of CO2 if you increase CO2. If you have only Z time, say the double what was Z time CO2, and let the weather going, this is here a 100-year run, then you have no real change. But if you have an strongly increasing CO2, then you really have an increase in the temperature. This was in the late 80s. Manabe, same age, by the way, as Hasselmann, as they became 90 years old this year, and both are alive, and I know Hasselmann is very active. He is from Tokyo, from Japan, but then went over to US, first to NOAA, and I think then later to Princeton. And he also developed a lot of models, rather realistic, in order to understand the influence, especially of CO2. And here is one result. I give only a very few. One result is he made such calculations for the thickness of ice. What happens if CO2 is increasing? If it's not increasing, if it's at the state, this was 1980, then you see a change, especially in the northern hemisphere, that in summer the ice becomes thinner and less in extension. In the lower, in the Antarctica, it's almost constant. But if you now have here the fourfold CO2, then you see a strong change, especially in summer. You have a strong change of ice thickness in summer. And you see also a reduction in the Antarctica. But the effect is stronger in the Arctic. And this was only modeling. And this is what has been now confirmed with real data. We see it now. And this was really also genius, was really a forecast of the qualitative behavior, not of the details, but of the qualitative behavior. And then he considered also the Atlantic Ocean. You know that we have this circulation like a conveyor belt, where we get from Mexico and also from Brazil partly warm water going upwards at the surface, bringing us such mild winters. What we call mild winters, for you are strong winters, I know, but for us are mild winters, especially in UK. And this has to do with the speed of this conveyor belt, if you wish, and of the freshwater activity. If the CO2 is not changing, you have almost the same kind of activity of this conveyor belt. But if you have again a fourfold CO2, then you have a decrease of this velocity of this conveyor belt, and you come then even to such a point where you are not zero, but only slightly above zero. That means it's a strong slowing of the speed of the velocity. And this is what we call now these days a tipping point. And this is one of the dangerous tipping points one we could have if this conveyor belt in the Atlantic becomes much slower and maybe even stops. This would change our climate completely. This he found also, and these were only to give you two milestones they found. They did much more, and I would say it's really it's very good that they got the Nobel Prize, and you can compare their results with those of other Nobel Prize winners. There is no discussion about. And my some personal experience with Klaus Hasselmann is he was member of a scientific advisory board of a EU project I had. And this was on what I will explain in the following on climate networks. And we started this about 12, 13 years ago. And when you start a new thing, then people do not believe or laugh about you and are criticizing you. And so this is normal. But Hasselmann, he looked at this, asked very good questions, very hard and strong questions. And then after all, he told me, you should go ahead. This way it has much potential. Although that time we had not much results. It was only the very first, this was 10 years ago, and I'm really proud. And this was also encouraged me to go ahead, let me say. So but now let me explain a bit what climate networks are and what one can do with them. First, of course, this is work with many people. Here is first my group in Potsdam at PIC, but also several people, they were my PhD students now at various places. But of course, you need also experts. I'm a physicist and mathematician, not a climatologist. And I was lucky to have to meet very good and very with high expertise colleagues from climatology, with whom we collaborated, and also from Brazil. I have long-standing collaboration with José Rengo, Albert Macau, and also with Enrique and several others, but with these climate networks, mainly to mention these, but also with several other people from different areas, which contributed a lot and helped us a lot to go the right way with climate interpretations. So first, I will explain a bit what climate networks are, and then we will go to extreme events, and I will try to convince you that these climate networks are really helpful for some questions with extreme climate events. If I have time, I can also discuss a few challenges for climatology at all. We have here, what we are studying is a system Earth. This is a very complex system. As a brain, maybe I would say these are the two most complex systems I know, at least. Maybe there are also others. Astrophysicists argue that the universe is the most complex system, but also system Earth is very complex. And but here we have, especially in the atmosphere, we do not have a simple network structure as we have in a social network. In social network, all you which are listening me now, you know each other, I know someone of you, and then we interact, and one can consider this as a network and how information flow is going. But in this case, in atmosphere, we have, of course, this is a continuous system. And we call then, this is a flow system, and we call what we study now flow networks. And what we try to do now is to look whether there is a backbone underlying a climate system. And one can consider this as some kind of discretization. That means you have these PDEs and you have to discretize. With finite difference method, with Gayorkin, when you develop after some basic functions or so, these are well-known techniques and work very well, but we go a bit other way. We look for arbitrary interactions. This is our kind of discretization. And then we try to see, can we then solve some problems in a bit better way than with the usual way. And how are we going this? Here is our Earth, say the surface or in the atmosphere. And we have here a network of observational sites, and we consider each subregion as a node in our network. And this is characterized by typical behavior and time. And we have time series, we have precipitation, we have temperature, we have wind, humidity, etc. These are our time series at the different positions. Say here is one at I, J, and K. And then we consider, this is an important step now, whether there is an interaction between two of such. We consider pairwise first. And if there is an interaction, usually correlation is not enough. One has to look for some nonlinear mutual information, or we go for extreme events, the so-called event synchronization. And if this interaction or causality is significant, then we make a connection between, here in this case, I and K. Then we make a connection. That is the way we construct the network. And this is described by the adjacency matrix Aij. If there is a 1, we have a connection, otherwise 0. One can put here also continuous values when one includes also the weights. This is possible. Then we have the network, as here is such a case of network. And then we try to use techniques from network science and look whether they can help in understanding. What one can get immediately is to infer long-range connections. They are called teleconnections in climatology. And here this is shown for a network with about 100,000, more than 100,000 nodes, edges. And here are the strongest connections shown. And you see a lot is equator-wise, but also along the oceans. There are the strongest connections. And already this is for the climatologist of interest to get such visualization of the strongest connections. And here you see already what I mean with the kind of discretization. And these are only the strongest. We have also other ones, of course. Also this is already very helpful. One has, I have to mention, one has to take care very carefully the result concerning artifacts, as a lot statistical analysis has to be done before taking a connection as a real connection. And as one result, which looks simple, but it's not so simple as it looks, the question is, how is the activity, the ENSO, El Nino Southern Oscillation activity from the Pacific going, or dynamics, to the India, to the monsoon area, to the Indian subcontinent. When we consider this network analysis, we find different pathways, different routes from here to here. And then we consider what is the most probable one with our methods, and we find that it's this way. Here going to this and then going to the Indian subcontinent. That means it's going via the Indonesian archipelago. And already this result was not known and was not clear. And we could really publish this in a good, very good journal. And this is a typical result you can get. But now let me go to extreme events. This is the main focus. And I will refer to another great physicist, Richard Feynman, we all know. And he had once the motto, test of science is its ability to predict. It's a very strong restriction, a very strong goal we see. And let's see whether we can fulfill this. As I mentioned, forecasting weather climate is a long-lasting challenge. We have now the so-called global circulation models, which are followers of Richardson's approach, which work very well, make very good weather prediction, but they have the drawback that their prediction horizon is maximum 2 weeks. And you cannot predict longer with these GCMs, and several extreme events are not predictable at all with the GCMs. Whoever did it in UK, in Germany, in US, or in Brazil, one cannot be better, and they are strongly working together. One example are strong rainfall in Bolivia area. I will come to this later. So, and the question is now, can we, with our complex network approach, going beyond 2 weeks, at least in some cases? And for this, we have developed the event synchronization technique, and this is especially for precipitation. Because precipitation, as you know, we have almost no place on Earth where you have everyday precipitation. Also you have gaps, zero precipitation. This is horrible for all statisticians if you have zeros in a time series. And therefore we had to avoid these zeros, and therefore we considered only the strongest events. Here, in this case, are the 10% strongest events. These are above this threshold. And what we are now consider is whether such strong events happens almost at the same time as here or as here. And not exactly at the same time, because if you have precipitation at some region, you cannot expect that in another region is exactly at the same day. We have to consider some windows in time. They depend on the size of the area we consider. It can be plus minus 3 days, plus minus 7 days. This is the area we consider. And if this synchronization happened not only once, but significantly enough, then we make again a connection. As this is a kind of construction of the network, that we have two regions, two nodes in our language, have here a time series here. We consider then this event synchronization. If this is significant, we make again a 1 for these two components I and j, otherwise 0. And then we have a network and can then use our network measures. By the way, this technique in principle was first developed in neuroscience. And there are many, because Enrique mentioned that I also analyzed physiological time series. They are so similar to climatological and other time series. Therefore, it's no problem to go also to this. So now let me show a result. We used here a global pattern. We were interested in a global pattern of teleconnections of strong rainfall. As we considered only strong rainfall. And the best data from covering a rather large area in a very regular manner are satellite data. And we use TRIM, so-called TRIM data as a satellite. And this started in '98. That's the drawback. You cannot go much further back because satellites started only later, very good satellites. But the advantage is we have a very good resolution. Spatial resolution means we have more than 500,000 grid cells. And we take daily data and we considered from the 10th to the 1% strongest events. And now we have this pairwise comparison. That means we have to make 10 to 11 comparisons. This looks a lot, but it is not with modern computers. This is not the problem. The problem is different. The problem is a so-called multiple comparison problem. Because if we have one position, time series rainfall at one position, we have to compare it with all the other positions, always the same data. And this has to be done with all the positions. That means we have to take the data again and again, and this is called multiple comparisons. And this is a classic problem in statistics, and they can cause artifacts, which one has to avoid. Also it looks there that some actions are significant, but they are not. And therefore one has to make some corrections. There are classical corrections as Bonferroni, but they are too conservative. And therefore we had to develop another one. If we would take this one, no, we would not find any connections, and this could not be. And our approach, this took us most time for this paper. And this paper was, by the way, published in Nature, and it was the first paper on climate networks in Nature at all. And what we considered is not only a simple pairwise connection, interaction, but we looked whether we can find also significant bundles or significant coherent spatial patterns. Because the rain cannot jump from region A to another region, it must have a pathway. And this is what we try to identify, and we consider a connection only significant if we can find some indications for a pathway. And for statisticians, this is some kind of generalized conditional causality. So, and now what do we get out from this? This I show you, we take as one area, sub-area, northern India and Himalaya. This is this little red dot here. And if we do not make corrections, it looks so that this area is connected with all the other ones from the strong rainfall viewpoint. But after the correction, which I mentioned, we have much less, and the shaded things should be also neglected. That means much less connections remain as real, as significant ones. And this looks therefore very probable what we have done. And we have distinguished a bit the rather short range and the long range connections. And you see also, as expected, there's a lot with the nearby areas, but we find even connections to both Americas. To South America was not such a surprise, but to North America, to Europe, and a lot also to the Southern Hemisphere, because this is in the Northern Hemisphere. So, and then physicists like scaling. We looked then what is with the probability density function of these connections independence on the distance. Also if there's zero distance, if distance is increasing, what is then the probability that a connection can occur, a connection occurs? And this is then for all starting points. It's not only Himalaya and northern India. And this is shown here in a double logarithmic presentation. And you see here such a scaling. Power law scaling is a bit different from linear. It's not exactly one, it's a bit different, but this is not so important. And this is as expected, the probability becomes less when the distances become larger. But then seemingly a surprise occurs at this point, because here we have an increase, not going to this maximum, but nevertheless an increase of probability. And this happened for all these percentiles, and we played a lot with the parameters. This is really a stable result. And then we asked what could be the reason. And this is then also rather simple when you have it. This is here reflected by the regional weather system, which is mainly due to thermodynamics. And for the description, thermodynamic interactions are important. And the longer ones are the teleconnections. And they have to do with large scale circulation dynamics, and here especially the Rossby waves. And this one could explain in general. And then we looked also for further details. Can we find some special insights? And we considered then some motion from more westwards to eastwards in the northern hemisphere, from Europe to Eastern Asia. And there, from the Rossby waves, one knows that there is a so-called Silk Road pattern. And we analyzed now our strong rainfall data from this network approach, and also found such Silk Road pattern. That means that these Rossby waves modulate in some sense the strong rainfall, and therefore induce some long-range effect, some teleconnections. And this could really open a door for predictions of maybe strong rainfall in Eastern Asia after a strong rainfall in India happened also. To summarize this, we have these two scaling laws. 2,500 kilometers is the breaking. We could also uncover linkages, very long linkages, and we think that this kind of analysis really opened new ways for prediction of extreme rainfall events. Okay, now let's go to some special examples. The first, Indian monsoon. You know that the Indian summer monsoon has vital importance for India. And they need it not too strong, not too weak, but normal they like most, of course. But here we consider a very special problem. This is the onset of Indian summer monsoon. The question is, can we forecast the onset of Indian summer monsoon as early as possible? Because this is very important for agriculture, most important for agriculture, to bring out the seed. If you bring out too early, then all is dying out because it's dry, as this farmer had. He lost all. If you bring out too late, then the seed cannot develop roots, and all the plants, the little plants, are washed out, or even seeds. Also one should have a rather small window early enough to bring out the seed. This is a question. And we take here several data. We take again our nice trim data, but they are not going too fast back. There is then another database of rainfall, it's the so-called Aphrodite database, which are almost real data, a bit interpolated, but not too much. And we also use typical other measures as temperature, pressure, wind, etc. So, and then we take, it's not enough to have only complex network analysis. This is the first step. And with this step, we identify the most sensitive areas, which feel first the onset, the coming summer monsoon. It was via this event synchronization. And then at the next step, we use another typical phenomenon of nonlinear dynamics. This is called pre-bifurcational enhancement of fluctuations. That means if you have a fluctuation or a phase transition or whatever, which word you use, and you give the same amount of noise on this for the different parameters. First, you are very far from the bifurcation, then you are going closer and closer to the bifurcation, and it's known from nonlinear dynamics that this noise will be amplified. That means the variance of the original noise becomes increasing as closer you are going to the bifurcation point. This we use as the next point, and then we use also a very special and typical behavior of the climate there, temperature and humidity. Okay, and with this, I will show you a few more details, but let me give the main result first. We can really extend the prediction horizon, and we can now estimate or forecast the onset of the summer monsoon 40 days before the onset. And when we look into the past, as where we know the future, this is what one first, how one checks the method, we have a success rate of 74%. But in the learning, we have, of course, the future not included, only to be sure. 74%, which is not bad, and even for the withdrawal is longer. But let's here concentrate on the onset. And what is it in more special case? The sensitive areas are we identify as North Pakistan and the Eastern Ghats. Usually Kerala, this area is considered because the monsoon comes this way, arrives at Kerala. And of course, makes sense that one think if we can forecast in Kerala, then it's done almost. But this is not the most sensitive area. When we consider these two areas, we are really much better. And here you see then the growth of the variance of fluctuations of these, here is of temperature. And you see that they are really increasing strongly as closer we come to the onset of the summer monsoon. And this we use also for estimating the onset, to look back. And you see, if you consider the same for whole India, you see no effect. This is already one indication by these two areas are so sensitive. This is more detail. So, and then this we published in early 2016, and we were asked then make real-time forecast, where the future is unknown. We did this now a few times from 16 till 21, and we were successful in each year. This is a bit a surprise because in average, we can have only 74%. Maybe due to climate change, it's now easier to forecast. This is unclear. But the limit is we cannot yet forecast the intensity, also how strong the summer monsoon will be. We are working now with the Indian Institute of Meteorology in Pune and with others to improve this and to include our approach into their operational forecast system, and hopefully this will then be better. So another, let me be a bit shorter, is South America. We took the same data, and here the problem is extreme rainfall in Bolivia, because this induces floods and landslides, which have caused a strong damage. And so far is no pre-warning system. And we made then an analysis with Jose, especially strongly involved, and Enrique was also involved. And we studied strong rainfall events in the Buenos Aires, Montevideo area and followed up. And what we found, this is better seen here, is that it goes this way, north-westwards. And then you have here this very strong rainfall. And then there was, this needs about 2 days, this way. Then there was a strong debate among us why rain can come from south. Usually it's coming from north. And so you know this much better than me. But we had then the hypothesis that again Rossby waves are coming and bringing cold wind from the Antarctica to South America, to this area. And then this south wind acts like a carrier and takes this humidity northwestwards. And this was a hypothesis. And then we looked in the details of each of these events and found that 60% of all these strong rainfall events followed this hypothesis. And during El Nino, even 90%. Also it's not bad. And that means here forecast of 2 days. But 2 days is better than 0. And then very recently, we also followed tropical cyclones, which are very strong indicators and causes of strong climate events and extreme events. And we tried to follow up such rather short-lived phenomena as a cyclone with our network methods. Then we have, of course, to do with evolving methods. That means rather small windows. We calculate the networks step by step and then calculate typical parameters as clustering coefficient and can then indeed follow up these cyclones. And this opens also a way. This was published recently, maybe I think it's not visible in Climate Dynamics a few weeks ago. And this should also open a way for predicting strong climate events. And we did this also for typhoons and extreme rainfall, especially in Japan. There are areas of very strong landslides. And we found with this approach that they are mainly due to the monsoon-like phenomena and not so much from the other tropical storms. This was also a bit surprising. Also you see that one can do something with this climate network approach, but I have also to say that this approach is in its infancy. There are many open problems. We will go for other extreme events also to Europe. We are strongly working, and we are also working now in North America, also not only in these very in tropical areas and subtropical. We will include several components. This leads then to multi-layer networks and also several layers in the atmosphere. And we will also use, we are on the way to use machine learning to improve the speed. We will not use machine learning as a blind tool. Then you always get out something, but we will use it for some subtask where it really makes sense. We have also published papers about, in the beginning, most of you are physicists, I know. In the beginning, we could publish in physics because there we were known a bit, but we had no chance with the first results to go to real climate journals. This really took us some years, but then now it's well accepted. And you see, even to go to Nature, it took us almost 10 years. One has to have really some breeze with new approaches. Enrique, do I have 5 minutes to talk a bit about further challenges? Or
yes, you can go ahead.
As to go now a bit beyond this, to give you only some challenges in climatology and meteorology. One problem are so-called tipping points or tipping areas. These are areas as the Amazon rainforest. You know, when one make too much deforestation, there is a strong danger that the whole system will tip, will have a phase transition. The same is what I talked about the Atlantic, this thermohaline circulation. We have this with both poles, melting of ice. We have this with Himalaya, with boreal forest. Then a lot of, due to melting, a lot of methane is coming out. And we have the coral reefs summer monsoon. And all these areas mentioned here, or phenomena, if you wish, there is some danger that they change qualitatively, that we will have a phase transition. And the question is then, when one tips, will it be a domino-like effect, or will it only an isolated effect? Here is only shown if we have a melting of the Arctic sea ice, much more reduction in area, then it's expected that we have really a domino-like effect. And but now it's not clear how far we are from this tipping, and whether there are clear precursor phenomena. And this, you see, this looks like a network, and we also tried, and others also, to consider this from a network perspective. We have a lot of extreme events. It's a bit questionable whether we have more extreme events, but what is not questionable is that the extreme events becoming more extreme, becoming stronger. We have these very strong wildfires in California. We had to have heat waves in Europe, now almost every year. We had floods in Kerala in 2 years in a sequence, which is very extreme. Snowfall in Syracuse, and typhoons in Japan, and several other things. And one problem I would like to emphasize finally is one consequence would be sea level rise. And you know that many big cities and a lot of population is living very close to the sea, to the oceans. And it's well known, especially in Bangladesh area, which has only a little, they are only a little above the sea level, and some increase will have huge effects. And you see here this in pink, you see all these big cities which have strong, there's a strong danger that they become flooded if the sea level rises more and more, and this has to be expected. And yeah, with this, I would like to stop. You see, there are a lot of dangers. We really have to do something and have to be careful. But on the other hand, we also have to dig much deeper into the climatology to understand much better what are the most dangerous things, what are the real causality, and where we can do something, and what we have really to reduce CO2, methane, and whatever, and also the land use and so. But with this, I would like to finish, and please, I'm hoping for questions.
Thank you, Jurgen, for this excellent talk. And I'm sure there will be questions. I'm not sure if Paulo wants to handle those, or if I should go ahead and do it. Paulo?
Please go ahead, Henrique. I'll just feed you with questions from YouTube if there are.
Okay, so I'd like to ask the audience if someone has questions to Jurgen. So Dave is made a question on the chat, and I see that Gustavo Burgman raised a hand. So let me ask first this one. Jurgen, do you think that the icy albedo feedback is enough to explain the Arctic amplification?
I'm not so specialist in ice, but this is of course a basic phenomenon and the main phenomenon, but there are also other effects included. But this is really one of the basic phenomena.
Gustavo, I see that you have your hand raised, so open your mic. Yeah.
Yes. Hi. Thank you very much for this very, very illuminating presentation. Very interesting. And I'm just going to ask one question. Although I'm not from this area, and so I have many. But specifically, you mentioned at the end this question of this domino effect, right? And then my question is, how much data you need to actually understand whether this is really happening, and whether the direction of the domino effect starting in any of these nodes will also be a domino effect. How well do you understand this, considering the data you have?
Yeah, it's a very good question. This is one of the most open problems in climatology and one of the most discussed, and many people are working on this. We know already some things. The problem is to find interactions among these different areas. Also, I mean, physical interactions, physical laws among them. This is not so clear. One can describe with the whole PDEs, but you do not understand the real mechanism between. And this is what we are looking for now in order to find first so conceptual models, also simplified models, but which include the basic phenomena. And this is what people are looking for. We started as physicists taking some excitable system and then couple them. And then looking for some domino or not domino-like effects. This is the simplest thing, but one should really have a more refined description of these subsystems with a conceptual model as well as with the coupling. And both is a problem. It's strongly worked on this, but there are no, I do not see the real progress. There are many detailed results, but I think we should really do much more to understand this better. Also what is rather clear, I think, is that these coral reefs, they have not so strong domino effect because they are already dying out. Yeah? This is, we know, but it's very clear if this Arctic sea ice, then it's clear that this has a strong effect on the Atlantic thermohaline circulation because then not so much fresh water is coming again and again. And we know this also with the Amazon rainforest. Here we have to especially study the interaction with the ocean, more with the Atlantic, maybe also with the Pacific. Also one knows something, but to bring this into models, this is the point then. Yeah? You have to find good, simple enough, but not too simple models. And then to find also some physical coupling, not only a formal coupling, but a physical motivated coupling. And this is what people are looking now strongly for. And then to compare with some data. One knows something from the paleo, also how the climate was in the past. There were epochs where the Atlantic circulation stopped or was very slow. And therefore one could really see what happened there and what was the reason. This was of course not anthropogenic, was completely different, but we try also to infer some mechanisms from the paleo times.
Thank you. Excellent. Thank you very much.
Jurgen, the talk is being broadcasted to our YouTube channel as well, and we have maybe around 40 people watching over there, and we have some questions from those folks. So the first one is, could you explain how do you use a climate network to make a prediction?
Yes, this is also a very good question. Let me come. Let me come to this. Maybe here is easiest to explain. This in South America. We started here. We considered the rainfall and then network analysis. We could really follow up the pathway. We could identify the pathway. And this is this one. Yeah, we are going upwards this way, and from this we could infer this. And this was then only a description in some sense. But a description is not enough. One needs then also a mechanism. And this is not coming out of the network. We get only some hints from the network. And for this, you need then more insight from experts. And this was then these Rossby waves, this hypothesis that they act as a carrier. And this we consider then, we proved this with the detailed weather conditions and found then that this is really, in many cases, a good hypothesis. Also it's not such a simple, straightforward way the first way with a network, you find some structure, some patterns, some dynamics, which was not known before. And then you have to understand. If you understood, then you have to look whether it has also a potential predictive power. And I showed you a few cases. It's not always. We cannot solve all problems. And this is really not a simple way, but it's really a subtle way to come then in the best case to forecast.
Right, great. We have another question here from Gustavo, also from YouTube. He wants to know more details about the type of networks that you use. He asks, what kind of node dynamics do you use in your model? Are these amplitude phase oscillators or something with additional complexity? And as synchronization concepts are being discussed, what kind of limit cycles are taking place at the local scale, right? So in what are the degrees of freedom build up the oscillators for temperature, rain, and etc.?
No, we made much simpler. What we did is a data-based construction of networks. This is the same people are doing in neuroscience from EEG or from MEG or such things. We consider only the data, and we argue there is some typical dynamics in it. It usually is not a simple limit cycle, because we do not have only the annual in the climate data, we have much more. And then we look for interrelations among these different time series, among these different data, and then we infer or construct the network from the data. This is all what I mentioned here, but then with, for instance, one would understand then also the mechanisms, and for this one should have then also models. And this is then the question, which kind of dynamics? Then we come to the question, which kind of dynamics one should put in. This is mainly the case for these tipping points. And there we used excitable systems, because sometimes it's really quiescent, sometimes you have real activity. One could also some smeared limit cycle, but in climate, this would be too simple, I suppose. We need, for climate, if we go to models, you have then also to have a good hypothesis for a more complex behavior of which mimics such data, and then one could also look for dynamics, for the dynamics of networks where you put dynamics on the nodes. But our approach was here only data-based so far. And this is the next step when we go to models.
Right. And Professor Katisha here in the audience wants to make a question. Katisha, please open your mic. And
hello, Jurgen. Nice to see you. Thank you for this beautiful colloquium. I was wondering if you have tested this method of building up a network on much simpler problems, such as, for example, if you look at the hydrodynamic transition to turbulence on an experimental system like a Taylor-Couette cell, and see if you can predict the turbulence that is going to occur and build a network, like, I mean, approach it in the same way, and see, where you can measure and you can make a lot of experiments.
So what we did it even simpler. We put simple models, which really simple models, 2D models, which mimic some flows, and also then changes of the flows, as phase transitions, going to turbulence, if you wish. And then we applied this simulated data from such simple models, and then we applied our techniques and look whether we can identify such transitions, whether we can identify the crucial points where such things happen. And this looks very promising. We have not, for such experiments, what we are doing now with the experiments is with combustion experiments, combustion engines. there you have the big problem that there are often instabilities. And in rockets or in airplanes, these are not so nice if you have instabilities there. And we have colleagues in India, Sujit is his name. He has really very nice experimental apparatus for such combustion machine. He measures and we analyze these data and we found then precursor phenomena when you come, there's a periodic behavior is a crazy thing, when you are close to the periodic behavior and also there our method works that we can identify. But for such simple experiments we have not done because we have not connected people with good experimental devices in this manner. That's the only reason.
Oh, okay, thank you.
But this is a good point. Yeah, but we did it with models which are very similar to the situation which you described for experiments.
Thanks.
Jürgen, we have another question here. Katisha, do you still have further questions?
No. That was
so we have another question here from the audience on YouTube. And this one is about extreme events and their frequency. Could you comment on what indications do you have, if you have or not, whether the extreme events are becoming more frequent or not?
Also we have clear indications that the extreme
are becoming more frequent.
No, we have clear indications that they are becoming stronger. More frequent is a bit, it depends on the event. Some it's already clear, not all. This is a bit more questionable, but the strength of the extreme events has become really substantially stronger. This is clear now. Also, to give you, in some sense, they are also more frequent. We have in Germany had the so-called century flood. And this was, I think, 3 years in a row, a century flood. And then it's clear they become more frequent, more than the 100-year one. But we had, for instance, in Germany, maybe you heard about this in summer, this very strong landslides with a lot of victims and so many dead people. There, the reason was a very strong local rainfall, extremely strong.
There is someone here on the chat on Zoom asking for more details about one of the studies that you mentioned, the one that you mentioned, the lags in weeks between ENSO and the Indian Ocean and the Arabic Peninsula. If you remember the title of the journal, so that I think it's from 2015 in Nature Communications.
Yeah. There is in Nature Communication 2015. He or she can send me an email, then I give you the full citation. No problem.
Okay, and I have a question myself, Jürgen. Can you, you mentioned a lot of very interesting results that you and your collaborators have been able to achieve over the last 10, 15 years. But you finish your talk in saying that this area of science is still in its infancy, right? And that there is still a lot that we need to learn. Could you comment on that? Like, what are some of the major open points that you think the young people in the audience could be paying attention to?
Yes, there are really, let me go through. Yeah, also one point is from the methodological. There are really important problems from the method. If we look, for instance, for extreme events with precipitation and extreme events in temperature, say heat waves. These are, the temperature is rather continuous, rainfall is more point-like. And the question is then how to bring this together. One is very interested now in so-called compound events. That means that you have in one area, or maybe in two areas, almost simultaneously a heat wave and say a very strong rainfall also. Yeah, rainfall, that is not so good with this, or maybe a very strong storm and a very strong rainfall. These as compound events, or you have very strong rainfall in two rather different places. And the question is then, how can we understand this from this network viewpoint? And I think this is also one, it's not enough to consider only pairwise interactions. You have to look for triplets and maybe more and more. And this is a strong statistical problem. And this is one important point. And then also if you compare then rainfall with storm is also more continuous, then another problem, how to make an interaction among both. And this is some kind of problems, multi-layer problems, as one has to use also different layers in the atmosphere, different parameters is a huge problem, how to bring this together. This is one, yeah, let me say, one type of problems, more methodological, but the point is then also the modeling. We get something out of the networks. This was one of the questions. Can we create, based on these network constructions, can we create rather simple models? This would be some conceptual models for each node, and then the interactions we get from the networks to simulate some climate. This is a completely open problem. There are some ways now to learn nonlinear dynamics, to learn equations from data. This is from machine learning, but this is in the very beginning, and for noisy data and non-stationary data is very difficult. This is another problem. And yeah, maybe this is already, and of course, going for other extreme events and looking what is a real limit of these approaches. This I was asked, can we increase this with a monsoon beyond 40 days? I do not think so, but maybe. Also there are limits, of course. This is no questions. And this has to be studied in much more detail. And maybe one can also find some criteria about forecasting what could be possible.
And thanks. And we have one final question here, I believe. This is from Arturo Sanchez. For the time series in which you use only values above the 99 percentile, I think it's that study where you show the extreme events in South America. He asks, which is the advantage of using the event synchronization instead of cross-correlation?
Yes, this event synchronization is a nonlinear method, because this kind of comparison is some, if you wish, synchronization analysis, which is also a nonlinear effect. And with cross-correlation, people did, and we also did, and there you get no clear results, no clear causality. And this is a strong indication that is very nonlinear. And with the correlation, you have also the problem with the rainfall data that you have so many zeros. It looks a bit trivial, but it's a big problem in statistics in a time series when you have so many zeros. They disturb all statistics. And this is the advantage of event synchronization. They do not care. It's only caring about the strong events.
And it appears that people are not wanting to leave. So we have another question here. This is from Enver Ramirez, and he mentions that the connections between 2 points, like 2 nodes on the Earth, right? These could depend on the different seasons, or even on the strength of the related parameters. For example, not all El Niño impact equally onto the precipitation in the same way. So how to capture those types of connections?
Yeah, this is right. And we try to consider only windows as short as possible, but we need some windows lengths. And as in the case of South America, and also this in the case of this monsoon, we only considered the season, the monsoon season, also only the months December, January, February. In this case, we put all data as we merged all these 3 months from one year to the other to one time series, because otherwise the time series would not be long enough. This is a technical reason. We hope also that's a big problem, also a methodological problem, to go to shorter time series, that we have only really the 3 months in 1 year. We know that this is a very non-stationary system, and each year is somewhat different. But here it was a hope to have basic phenomena see more or less in the same manner over these years.
And Jürgen, I have here one final question, I believe now. It's from Gustavo Wiedenhecker. And I didn't ask it before, but he mentions that from your experience after dealing with such massive data sets, what's your take on our physical sensor network capacities? Do you identify clear bottlenecks, maybe on sensitivity or spatial and temporal scales of sampling that impose limitations in the kind of things that you can do with the networks, right, from the observations point of view?
Very, very good question, because in climate, you have not only one, as I mentioned already, not only the annual period or the daily, you have a lot of periods, and not only peaks, but rather broadband behavior and a lot of time scales. This is in time, and in space, you also have different kind of scaling behavior. And what we also started and was already a bit successful to use wavelets to combine different scales. That means to construct a network via different scales. Is there an interaction among the different scales? This is how we try to treat this, of course, very typical problem. You have always such typical patterns in space and time, and how to describe them best. Wavelet seems to be a good form. There are also other forms, maybe also some from machine learning, some neural networks can present typical forms, and we try then to combine them in a network.
Thank you, Jürgen. I don't see any other questions, and I think it's about time that we close our colloquium. I thank you again, Jürgen, for accepting our invitation. It was a great talk that led to great discussion with everyone. And I'll just give the word to Paulo. Paulo?
I'd just like to thank you very much for this wonderful talk, and hope we can have you again sometime in person.
Okay, thank you very much.